myself Avivansh, and I'll be sharing my EPF7 proposal, that is implementing the light line protocol in Teku. My mentors for this are Paul and Ethan. So let's get started with the motivation. So Altair introduced the light client sync protocol. It lets resource constrained nodes verify proofs and signatures from the rotating sync committees, which rotate approximately once a day. The protocol has two sides: servers that generate and serve the data, and clients that consume it. Currently, Teku only implements part of the server side. The way it works is that a sync committee of 512 validators, which rotates roughly once a day, as I already mentioned, signs the head. That produces a signed header, and a light client verifies the aggregated signature against committee case it already had from a previous Merkle proof. The key point is that there is no RPC operator in the trust path. The trust is entirely reduced to a DLS signature, which comes from the stake validators, and it is checked locally. So currently, a partial server-side implementation is present in Teku, which was implemented by Rob back in cohort 3. Since then, Teku only serves the bootstrap. It does not serve anything regarding committee updates, finality updates, or optimistic updates. On top of that, the current implementation still reflects the Altair specs, and there have been several changes to the specs since then. The light client needs four things. The bootstrap gives it a trusted starting point, and that part is already implemented. But to actually follow the chain, uh, it needs updates to follow sync committees, finality updates to track the finalized checkpoint, and optimistic updates to track the latest head. And all those three components are currently missing from the client. So, regarding the scope of the project is entirely about the server side, like generating and serving the data across every relevant fork from Altair to Gloss. On the server side, which means generating updates from state, storing them so they survive pruning, and serving them over REST, gossip, and request response protocol. The client side, which means Teku acting as a light client, is not part of the project and is out of scope. So let us see how the data is generated. The three objects come from two different triggers. The optimistic update follows the latest head. Every slot we take the newest signed header, and the sync aggregate that signs it, with no dependence on finality at all. And that is what lets a client stay at the tip. Apart from this, when a new checkpoint is finalized, we build the finality update, which adds the finalized header and its proof on top. And once per sync committee period, we build the full update from state. Uh, this one carries the next sync committee, and uh, we have a function called is better update in the spec, which is entirely there to decide which of the committee update is better, and which of the update should be stored locally. uh, so finality gets the finality update and the finalized part of the full update, but the optimistic update is produced continuously of the head. There is one subtlety that runs through the whole project. A few relevant fields like the sync committee sit at different position in the state tree at each fork due to addition, deletion, or modification of the fields in the state tree. Due to the change in position, their generalized indices change across the forks. So when generating an update, we have to select the correct fork layout. For example, the sync committee proof index is 54 in Altair and 86 in Electra, and it moves much deeper in Gloss, around in 2000s. So generation has to dispatch on the fork to pick the right proof index and layout. On storage, the historical updates have to be computed while the state still exists, and then stored, because once a node prunes that state, it cannot reconstruct them later, and we don't have any way to generate it again. So archive nodes can store this update, but we are focusing on pruning and minimal nodes too. The two possible paths to store these updates can be, either we store them on disk, using the flat SSD files, or either we create a new storage interface in the database used by the client. This part is currently being researched by me, and I'm currently uh, understanding the trade-offs for both the approach. Uh, so the possible challenges could be, firstly, the logic for picking the best update has some non-obvious edge cases. This part needs thorough testing. And as I already told you, the pruned and minimal nodes lack historical data. A storage mechanism needs to be developed where the data can be kept and kept persistently. Also, again, I told you the changes across forks in the container structure and also the generalized indexing uh, is a bit problematic and needs thorough testing. Now, coming to the roadmap, out of all the five phases I mentioned, the phase one is complete and the PR also got merged. If time permits, I would love to extend this project to implement the decentralized serial checkpoint sync in Teku, and Ethan is mentoring that part of the project. Success criteria looks like all the REST endpoints, there are four of them, are working and spec compliant. The finality and optimistic updates can be broadcasted via the gossip topics, and any peer requests are answered directly via the regress protocol. Also, the implementation passes all the relevant tests and interopes with light lines syncing from other PNs. So yeah, that was all from my side. I would love to hear any questions, feedback, or any suggestions.
Oh, three fellows. Give me a sec. Okay, does that work? Somebody signal. Nice. Thank you very much. Awesome. So, oh yeah, yeah. Sorry for that. Sweet. So, fellows, I'm going to present my project proposal for post-quantum stealth address protocol. Small disclosure in the beginning that most of the existing research was already done by some brilliant folks. And my area would be to specifically analyze how such protocol can be moved to be an extension schema for Ethereum stealth addresses, and to be for everybody to be on the same page. Just very briefly, introducing it to some steps that will be important in the future. So everything starts with the recipient. He gets some hash, publish that into the registry, and then once the sender wants to create a new address for the recipient. They basically doing some public uh, key exchange and using announcements to exchange that data either on chain or off chain. And then later, some more magic is being applied to top of it to derive the actual spending key and move the funds, but it's slightly outside of the scope, and we'll talk about that on the next slide. What is important for us at the moment is the announcement scanning mechanism, particularly because there is no better way to discover all the user assets except of discovering linearly all the existing events. And even though the data is encrypted, it's still being available publicly for harvesting now and decoding later, which is the primary issue that that I'll be exploring. For the spending side, everything is already planned on the protocol level with the frame transactions, and once those are going to hit the execution layer, the spending will be automatically solved. However, even now, from Kahaku SDK, we have some experimental implementations of accounts with Sphinx or the Lithium schemas that will be used. I approximated that to be, oh, sorry. Oh, maybe, okay, let me try to do that all the way around, like this. Okay, is it better? Nice. Yeah, sorry about that. So basically, not that many protocols already exist and successfully implement stealth addresses on chain. They have different types of improvements, but we are primarily focusing on the key exchange and the problem of harvesting now and decoding later. However, this could not be the most popular choice for preserving user privacy, but it's still being referenced for some of the upcoming research for native UTXOs, for example, as the way to pass some additional data together with the spending node. So this is the statement from postquantumethereum.org, a very good resource to get into the current state of things. And basically, all the users who are currently using post-quantum stealth address protocols who are exposing transactions publicly are sensitive for collecting the data and decoding it later. So existing research pretty much conducted that module variant of learning with errors, which is the latest commitment scheme, is the fastest, and it's probably the good trade-off also for the key size, so we'll just stick to that. As I said, signature migration is not really much of our concern. It's going to be shipped sometime later in the future. What is really useful for us is the library VCVO, which we'll be using for producing machine-checked proofs of the correctness of the logic, and also some game-based simulation to prove properties of the stealth address protocol. Ideally, we would also want to have some agility in key exchange, but except Kyber, it doesn't seem like there are any obvious choices that we can use. However, the gas spending on the post-quantum signatures, which is currently like around 8 million gas, can be temporarily improved by using the zero-knowledge proofs instead of the actual signature, by still providing the good future proof guarantees to the users, but not making them spend 8 million gas for each transaction. And ideally, if everything goes well with trustless locks indexing A304, it also would be a great showcase example how actually that would empower these applications. If we look at the post-quantum stealth address protocol, it looks exactly the same. The process did not change even a little, except of if previously that was 2 private keys and public keys, now it's 3 of them. And the key exchange, like kind of decoding process is slightly different, but it's mostly a technical detail that I'll not be covering here. So for the actual state of things, I got a successful proof of concept running on Sepolia with Kahaku account for spending, where I could actually provide you the info about the gas costs. Getting more familiar with the Lean4 and VCVO tooling that I'll be using for the rest of the cohort, as I'm really fresh to it. Also started comparing the other not so popular algorithms for key discovery. You can see results on the right. Just even from the brief look, it looks pretty obvious what the solution would include. GitHub repo is in progress. I'm gonna keep that up to date in my dev updates. And the successful outcome of this project would be to have a proposed extension, or at least a research post about the findings and the proposed schema to be used. If there will be some progress on both frame transactions and trustless locks indexing, that would be just amazing. That's awesome. As the outcome, it will be a reference library in the publicly available repository. And additionally, what original schema did not include, but I think it could be useful for institutional Ethereum, is the ownership proofs for such stealth addresses, for travel rules, and so on. That's pretty much it. A couple of links, my weekly updates, GitHub, when you can find the repo in a couple of days. Couple of good papers I can definitely recommend. Vitalik's very old guide into the stealth addresses, some of the new stuff for native UTXO. And that's pretty much it from my side. Yeah, thanks everybody for attention.
Hey, okay. Yeah, is my screen visible? All right, great. So yeah, hey everyone, I'm Vansh, and for the EPF, I'll be working on implementing AIP 8304 in Geth. The goal of 8304 and this project is to basically make Ethereum logs verifiable today. So whenever a wallet wants to show your token balance or transaction history, right now it has to trust whoever answers the RPC request. Uh, this project's aim is to basically remove that trust assumption by making log queries cryptographically verifiable while also staying compatible with the existing protocol. So the problem that exists right now is that let's say a wallet wants to display every transfer event for your address. Today there are really only three options. The first is running an archive node that works, but it's expensive and completely unrealistic for let's say a mobile wallet. The second is using an indexing service or an RPC provider. That's what almost everyone does today, but you're trusting them to return every matching log and not silently omit anything. The third option is checking Ethereum's logs Bloom filter that can tell you which blocks might contain matching logs. But Bloom filters have false positives, and more importantly, they cannot prove completeness. That last point about Bloom filters is a core issue. Even if every log returned by the RPC is genuine, you still have no way to know whether another matching log was left out. Uh, this was already solved for state. So let's say if someone tells me my account balance is 5 ETH, I can ask for a Merkle proof against the state root and verify it myself. Logs don't have an equivalent proof today, and that's exactly what A304 is trying to fill. So through 8304, we're not trying to introduce a completely new mechanism. It follows a pattern that's pretty common in Ethereum. During the execution of every block, Geth builds sorted log index tables, and after the execution finishes, a system contract stores the root of these tables into Ethereum state. Since those roots are now part of the state, anyone who already trusts the state root, for example, let's say a light client receiving it from the consensus layer, it automatically trusts those table roots as well. From there, an RPC can return both the requested logs and proofs showing they're genuine and complete. Uh, an important design decision here is that nothing changes in the block header. The existing logs bloom filter stays exactly as it is. The index is simply added alongside it. But there's also another proposal in works to remove the bloom filter work as well. So yeah, what does verifying a log actually mean here? The index itself doesn't contain the entire log. Instead, it commits to the log's address, its topic, and its position inside the chain. And those pointers eventually lead us to the transaction receipt. The receipt is what contains the actual full log, including the data field. So verification happens as a chain of proofs. First, we prove the table root came from Ethereum state. Then we prove the relevant index entries belong to that table. Then those entries point us to a particular block in transaction. And finally, a receipt proof against the block's receipt root authenticate, a valid complete block. So yeah, the final receipt proof is important because 8304 intentionally does not commit directly to log data. It completely relies on the existing receipt structure for that part instead of duplicating information. So the index is organized into 5 levels, and each level covers progressively larger ranges of blocks. Inside every table, entries are sorted using the entry type, value, block number, transaction index, and log index. Uh, why are we sorting everything? Because all matching entries naturally become one continuous section of the table, so that makes the proofs much smaller. Instead of proving every individual match separately, you can prove one contiguous range together with the boundaries around it. So yeah, that kind of helps to prove not only inclusion but also completeness. So I already have a proof of concept running locally. Right now, it builds the first two table levels, it stores the roots during post execution, and exposes an experimental ETH underscore get log proof RPC. Uh, the remaining work is basically taking that prototype to production quality. So the first step would be replacing the like a simplified version that I implemented of fixed size entries with the variable length encoding defined in the specification. Uh, After that, I'll replace the current hashing approach with SSD materialization so the table roots match the specification. Then I'll implement the proper multi-block merge algorithm instead of today's placeholder kind of implementation that would activate all 5 table levels. And yeah, finally, I saw Zolt's implementation of 774B, and something really cool that he does, and it's also sensible to do it here, is to move everything from memory into into a file bagged ring buffer. It's also described in the AIP, and handle all the operational details like fork activation, sync recovery, restars, and reoff all back there. Uh, One key important architectural decision is separating the consensus part from proof serving. So the consensus path only computes the deterministic roots written into state. Everything needed to generate the RPC proofs lives in a separate database that can always be rebuilt from the canonical chain if necessary. On top of the index, you'll also have to build an experimental RPC. For now, I'm just going with pure let's go get logs of proof. Instead of returning only logs, it would return the logs together with everything needed to verify them locally. Uh, the proofs support three situations. So first is proving a return log really exists. Second is proving that no matching logs exist, and third, proving completeness, meaning every matching log has been returned. I'll also spin up a kurtosis devnet with get and members and try to generate realistic transactions using SO2 and verify that entire pipeline works end to end. The uh, The correctness check I'm most interested in is differential testing. If get an independent implementation both compute the same roots for the same chain history, that's like pretty strong evidence that the implementation matches as well. And it's great to see that there are so many 8.3 over implementations in different clients. So yeah, that should be pretty sorted. So yeah, the project is divided into multiple milestones as mentioned in my project proposal. The first is to finish kind of like getting the POC to an implementation stage that's actually workable and mergeable to in the core get repo. So that's something that I'm done with the milestone zero part of actually scoping out what the changes should be and also finishing up on a lot of these. So I'm kind of like halfway through milestone one right now. Then it's going to be building out the proof index and the RPC layer. After that, Stas just presented a while back. He's also interested on working on the on a verifier and an integration with VM. That would be really cool to see. And yeah, finally we'll validate everything on a devnet with testing and publish performance numbers together with the implementation. So yeah, to wrap up, yeah, the goal is basically to make Ethereum log queries verifiable without requiring users to trust on RPC providers. And yeah, thank you everyone for listening.
Yeah, hi. Let me share my screen. Yeah, I think it's visible now. Hi, guys. So I'm Jeff, and my EPF project proposal, like the project, I'll be doing the historical light client data backfill in prison, and which is like a tiny step of we toward the decentralized checkable sync, and I'm mentored by Ethan. And so first I'll talk about the checkpoint sync today is that most of the client doesn't replay the chain, like they get the states from the genesis and calculate all the state transitions things from genesis, and they just start from the recent finalized checkpoint, and your node just download the checkpoint state, and you start from it, and you range sync toward the head, and after that you just backfill it just to get the data before that. And it could start up in minutes instead of days. And it is like for the days, it's just sync from the genesis. And what does the checkpoint come from? It comes from the untrusted provider, like endpoint, RPC endpoint, and you just tell the endpoint, say, you give me the finalized state, and the provider gives the beacon state to you, and you just trust it blindly. So the problem here is that the provider could give you a fake state and route, and you just check this verification and you say, okay, this is correct, but it is actually not. And also the weak subjectivity things also will prevent you from syncing from a very long time ago. And yeah, so this is a problem, and how we fix it is that we just verify and we don't trust. So the way we do that is we are kind of borrowing the concept from light client. So we start from a small trusted block root, and which is easy to share and check. And we follow the light client updates period by period so that we could follow this verification in each period until we get the recent finalized state root. And when you get this state root, you just, okay, this is trusted. And then we can compare this with the hash tree root and compare it with the, the result calculated by from the untrusted provider. So why is this? Is because the light client message are tiny. They just have the headers and like committees, which is not a big deal. And the light client protocol also never ships the full states. So, which is, I would say it is very convenient to use this as the trust. Yeah. And here's the kind of like the trust chain of light client. So you get the root and you get the bootstrap, and you will do some verification here. But after that, you will get the update, which is includes the several things like nest committees and the sync committee signatures. If it is over uh, second, third, and yeah, you just repeat updating, verifying these updates for many times, and until you get things like p plus n, and then you will get the finalized header here, and just get the state root, and you just verify it. And the gap is that currently the providers doesn't serve the history. Well, we need this pipeline, but it's not very every period. It's like we need every period's best light client updates. So those providers, they just sync, they just checkpoint sync, and they just have the historical blocks, and they don't have the post dates, but the updates are from the post dates. So this is a problem. And also, like, you cannot use this endpoint as well. This is an API from Ethereum. And yeah, so this is why we need the light client data backfill. And it is harder than it looks, is that we don't just verify if this light client update is valid, but we have to choose like if it is the best update for that period, because the period is 8,192 slots, but we have to choose, use some logic to choose which is the best updates. And some untrusted source could serve a valid but inferior updates. And we just have to check all of these things in the in this protocol. So the result, like the solution will be using the block roots list. So here we will get in. Okay. So in the backfill, like a protocol, we have several rules like consumer, provider, receiver, and history provider. So a consumer is just like a fresh starting node, and begins from the roots and walk through the light client updates. And provider is that the node serving the states and the historical updates. And in our scope, in this project, we're using this receiver and historical provider. So receiver will be the node who wants to recover its own history in light client. And so it runs several verifier to get the data from the provider. And this is just the provider providing data. So here's the protocol. So receiver will send a request to the provider and said, I want this data, and we'll get back to here. So this data looks like this here. So I think the most important thing is the block rules here, because we have to check all of the data from the provider are correct, so that we need to check this. And yeah, so the second step will be pin the block roots list, and you will get the light client block data, which is like this. So the third step will be like, we have to check if the pin list, this one, is having the same result of the participation bits here. So if there's any missing slot, we will reject it. And there's multiple verification and checks we have to check here. And yeah, and the third step will be we will use the light client updates. We'll get multiple updates, and we will calculate all of those candidates through the is better update logic. And then if our local computation is equal to what the provider gives us, then I think the verification is done, and we could store this data into our database. So our project will be implementing and evaluate the one period backfill for like until Electra or Fulu in prison. So it will become like provider side focus, but also we have to do the verification as well. So yeah, and currently prison already has these. So luckily we have the SSC types, which is the Mercurization of the assist types, and also the live update generation and its better update ranking, the logic, and the finalized update persistence. Yeah, and those, and also the REST handlers. So luckily, we will have to do only the provider things here. And yeah, so you can see the verifier just have to like do those checks to until before everything touch to the database. So like you just reject like malicious input or duplicate input and check all the things here. Yeah. And here's our roadmap is that I think it's just like a high level step. And I think the plan might be changed because there are some changing in the protocol by Ethan. And I think I will discuss with him as well recently. And yeah, so it will become like I'm writing the interface first, and then write down the data, and then do the verification, and then do some E2E tests. And also, I think in the end, we were testing with the Nimbus client against the Prism. Yeah. And what success looks like would be the Prism will deterministically produce the valid historical artifacts like these artifacts. And yeah, and the verifier should get the same winner from the local and the provider. And also the writing a lot of tests to test the invalid inputs. Yeah. I think the most important would be the updates by range REST endpoint should serve the results. Yeah. And here's some challenge, but I think after discussing with Ethan, I think the proposal and the plan will be not changing a lot. Yeah. And here's some reference, and thank you.
Hi, Mario. Yeah, I'll share my screen now. Okay, you should be able to see. Can you see my screen? Okay. All right. So, hi everyone. My name is Rahima, and this is my project proposal together with Arish and Ia. And the problem is that if you want to join the Ethereum network today, what you have to do is trust a provider. It could be a URL or let's say Infura or a friend's node. You trust that particular provider to give you the correct beacon state from which you start to sync forward to date. So we are trying to fix that problem by making nodes join in a trust minimized way. So the process starts by the node having a trusted block root baked into it from start, and then using the Linux client sync protocol, the node syncs up to date by first requesting the Linux client bootstrap and then Linux client updates for each period, and then he arrives at a recent verified beacon block root. With that block root, he could request the state with cryptographic proof, proving that that state is actually part of the canonical picking state, and then it fetch the states in verifiable chunks, and then it eventually has everything in it to become a full node, and then it starts its duties from there onward. There is no trusted URL, no trusted provider, just cryptography and P2P. So why is this hard? The data we need isn't there. So the problem is data availability. Although Lighthouse already computes Light client proofs for each block during sync, but this is only persisted for recent blocks. So we have Light client updates, sync committee branches, and sync committee data, but they are missing from the DP for historical blocks. So now the Get Light client bootstrap also says there is no backfill mechanism. So the result is that a node that syncs from Genesis cannot help a new node bootstrap trustlessly because it doesn't have the historical data needed. So now the infrastructure is mostly ready in Lighthouse because we have the storage schema for Light clients updates, sync committee branches, and sync committee itself. And then there's also the ranking logic by its better updates and proof of computation. So we just need to actually run them for historical blocks, and we can see from this table what already exists and what is missing. And as I've said previously, what's missing is um, old data or historical data that a node could backfill. So I think Arish would take it up from here.
Yeah, so the phase one, it has two pieces. My piece would be the verification layer. Lighthouse has no formal way to verify that it's producing the correct Litecoin data. And there's a category of tests in Ethereum's official spec test suite called data collection tests, but Lighthouse just has no implementation of it. So I built the missing test handler. The load case reads the official spec test vectors, which is a starting chain state and a sequence of blocks, and it deserializes them. The case then imports each block into a real simulated Lighthouse chain, triggers the Light client cache to update, and verifies that the cache is truth against the truth values from Ethereum's Python reference implementation. Without this, there's no way to formally verify that Rohima's backfill work produces correct outputs. I have the draft PR open right now. I'm also going to be working on the phase three, researching that in parallel with my work, which is the beacon sync chunking protocol. And I'll be building that on ETAN's guidance that chunks should align with the SSZ tree structure. For example, fetching validators in ranges of 1,000 at a time. And I'll hand it off to Yi from now. You're muted. Yi, your mic is off.
Continue. And hello everyone, my name is Ye. And we all know that phase one already gave Lighthouse the historical lifetime data that it currently lacks. And with those updates and sync commit proof available, and I will now move to the consumer side. Yeah, Jeff and Abibash just mentioned is more about the provider side. So the phase two is different. It's the consumer side. It's about how a joining node can go from a verified Lightcan header and to a complete vacant state without trusting a checkpoint provider. So we can see that after the standard Lightcan sync, the joining node has a verified recent header, but there's not yet enough to initialize a full vacant node because it still needs to discover a suitable vacant state and verify its state root. So our target in phase two is to find a state root. And for this, the proposal introduced the light client vacant snapshot. And the snapshot, you can see the structure. The structure is small. It does not contain the state itself. And the proof tree is like this. First, the embedded light client update is verified using the normal light client rules. This gives the consumer an authenticated recent header. And then the two fields, the two Merkle branches connect that header to the target historical state. The first historical branch, it proves the relevant historical summary against the state committed by the verified header, and while the state branch proves that the target state root belongs to the summary. And it is highlighted that the target actually is deliberately historical rather than the current head state. Because sufficiently old state is more stable and more likely to be available from multiple peers while still being recent enough for practical forward sync. And here is phase two. Once this proves pass, the consumer has a trusted state root. And let's go for the phase three. It's about retrieving the files that match it. Its vacant state is basically to get the full vacant state. Yeah, because we all know that a vacant state is too large to retrieve efficiently because usually it will take thousands of megabytes, and one peer failure would force the consumer to restart the whole download. So instead, the state is divided into SSZ aligned subtricks, and for each chunk, the peer returns the payload, its position in the SSZ tree, and a Merkle branch. And this means chunk can be downloaded in parallel from different peers, and invalid data is rejected locally and can be requested again elsewhere. So after all the chunks are collected, the node reconstructs the vacant state and performs the final check. The final check is very clear. The reconstruct state's hash root must exactly equal to the target state root we gained in phase two. Yeah, and this is the phase three. And for the phase four, actually is the integration part. Is where the previous components are connected into one complete lighthouse startup. And for the first part is end-to-end test because we know that we have the three the about three phase. How the new pair joins, how the things verifies, and how it becomes a full node. And the second 2 point is about the connectedness and the regression testing. It's about the testing part. And yes, and of course, all the existing Lighthouse client the tests must continue to pass. So the new backfill and the snapshot pass do not practice the current light client behavior, and that's very important. And let's go for the last part, the success criteria. And for the minimum viable, it's about a reliable historical light client foundation. The foundation is about the lighthouse persists the required update and the sync commit branches and can serve historical bootstraps, survive restart, and pass the relevant consensus backtests. And for the stretch parts, the later milestone are a working snapshot endpoint, a state chunking prototype, and finally an end-to-end demonstration. Yes, and that's all. And to sum up, our goal is to help the node to sync with minimized trust. And yeah, thank you very much. Yes, and if anyone has some questions, you can just feel free.
Hello all. Can you hear me all right? Let me share my screen. Can you all see that? So I'm Charles. I'm here with Keshav, and we're going to be talking about creating optional execution proofs in Grandine. So today, consensus client cannot tell whether an execution payload is valid unless an execution client reruns it. And that's true for every node and every block. So let me show you why this is becoming urgent. Ethereum unfroze the gas limit in February 2025, and it's now at 60 million. Soon, possibly with Glamsterdam, it'll be 200 million, with a stated goal of 1 gigagas per second. But that ambition comes at a cost. Every execution client independently repeats the same computation to validate every payload, and that duplicated work grows with the gas limit. And because validation means re-execution, every validator must run an execution client alongside its consensus client. So the real question then is this: how do we scale L1 execution without pricing ordinary people out of running a node? Broad participation is a property we're not willing to trade away. So the fix has to break the link between the gas limit and the validation cost. And here's the main idea. We replace re-execution with proof verification. So in an execution proof is a cryptographic proof that a block payload is valid. Verification is cheap, and its cost barely changes as the gas limit grows. Re-execution scales with gas, verification does not. So I'm going to talk a little bit about EIP 8025 and how that works. So in this EIP, there are two primary roles. They're new. The first is approver. Runs the fully synchronized node, it has to run both clients, an execution client and a consensus client, and it produces signed execution proofs. A verifier checks proofs and attests to slots on that basis. So both must be active validators. The EIP also adds 4 primitives, SSE containers to bind a proof to a specific payload, recursive verification, which lets one execution proof cover the chain from a weak subjectivity checkpoint all the way to the head. This is actually new. I only learned about this on Monday. There's also, we need proofs to propagate over gossip subnets, a new subnet, and a new abstraction called the proof engine, which sits alongside the execution engine. Importantly, EIP 8025 requires no hard fork. It does not change core consensus. It's entirely opt-in. The main constraint is a ZKVM maturity. Real-time proving is not yet practical, so that limits adoption for now. So that's a protocol. And Keshav will show you the part we are committing to.
So in order to we have to scope the whole EIP, because the EIP is quite big and it involves both the prover and the verifier. So our main focus for the implementation on branding will be focused just on the verification part. We are going to just get the block that is in just the execution proof, gossip across the designated proof type subnets. So a proof type is a combination. A unique proof type is a combination of a guest program and a ZKVM. So it can be like a guest program can be RevM or EVM1, and ZKVM can be any ZKVM processing or other ZKVMs which are currently in the market. Uh, the next thing for the focus will be to verify the PLS signatures as a pre-verification, and to focus on that the proofs that are received are unique and not duplicated in the mesh, and also to bind those proofs to the designated payload so that there is a one-to-one relation. The other main focus will be to capture the proof and verify them, and uh, Upon verification, designate that if they are valid or invalid. The validity doesn't decide the consensus, as proof handling remains auxiliary. So it is not part of the consensus critical parts, and it is not going to change the fork choice as well. So it is not as of the optional execution proofs until the mandatory proofs arrive. The whole consensus critical parts that is related to the fork choice will all be uh, optional. The next thing is to regarding the established prefix validity. This we realize, like Charles said, this is something we realize from Francesco, who is the writer of the EIP. He said that they are going to deprecate the request response protocol for the EIP, and they are going to replace it with recursive proofs, so that only a single execution proof can verify uh, uh, and sync up to the head. So you go from the weak subjectivity checkpoint and you syncing it up to the head via a single execution process, which makes it a seamless process. What we are not going to focus for the Grandin implementation will be the internal execution proofs. That is something related to the execution clients, as well as the prover signing, which the prover, everything there that is connected via engine API, and that requires a prover's intervention. We are not going to focus on that. We are only going to focus on the verification part, as well as we are not going to invalidate any already accepted execution payloads, because anything that is verified by the execution client should not be intervened uh, 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 by the proofs. And the stretch goals, if time permits, we are going to work on these stretch goals as well. The part where we perform the proof generation request for proof engine, the task of validator signing and sharing the published proofs that they have already verified to propagate across the subnet, as well as the durable persistence of the proof state, so that the state persists across the slots as it passes. Now I will again give the mic to Charles to share the whole proof cycle that I quickly summarized in a short way. Charles?
Thanks, Keshav. So, yeah, a little bit about the proof cycle. So there are basically 5 steps. First, a proof arrives over gossip, and then we perform a deduplication check and also check that its signature is valid. And these are easy, low-cost checks that we want to do before we send it to the expensive verification step. Next, we bind the payload to the proof to the payload to see if it's one we've actually seen. Because if we haven't received the payload, we can't actually proceed further. We have to have both the proof and the payload. After that, the proof engine sends the proof to an external verifier for the cryptographic check. And for this, we're going to be using zkBoost, which is an EIP 8025 proof node implementation. Finally, we store its state and prune it if fork choice has moved on. And there are really 4 outcomes. So acceptance, which means republishing the proof, which is standard for gossip sub behavior. Rejected proofs are discarded. Fork choice never sees it. And here's how we plan to build it. So we'll be working over 15 weeks. There's 2 of us, and we have 6 milestones. We split the work by domain, so each of us builds depth in one area. I'll be working on verification and trust, so the data model, proof engine and verifier integration, the KVN policy, and the recursive extension when that's ready in hopefully about a month. Kshiv will be working on ingress validation, so signing primitives and the proof service, payload binding and gossip transport, validation outcomes, anchor advancement, and restart and recovery, all the ETH2 libp2p work. And in week 8, we'll be co-designing the interface between our two streams. And then both of our streams will come together for the final milestone, which is mainnet interoperability and demonstration, which we hope to do against an ETH proofs proof. Keshav, I'd like to hand it off to you to talk about like what success looks like.
So regarding the success, the main focus will be to not let any verified proof which is legit go waste. We must always propagate verified proofs ahead to other nodes, as well as the to prevent DDoS, we must stop the junk proofs, which so the major reason behind DDoS is proofs size is quite large. They are like 4 MBs. So the size, because of the big size and low adoption rate, as well as the current ZK VM ecosystem, there is a good enough chance for the DDoS. So in order to prevent them, there should be good verification checks for that as well. The second thing is every verified proof points to an accepted payload. So for every proof, there should be an execution payload attached to it, so that there's a one-to-one relation. As well as the next thing is to ensure that the current the way Ethereum currently works should also work the same even after the integration of the option execution tool. So the task of the engine API should work as is. The fourth is the K of N case, where we have to ensure that at least K of N proofs are verified successfully for the payload to be valid. Although again, validity doesn't matter, but for the future compatibility, we must focus on this particular aspect, as well as this is what diversity is for Ethereum. And the K of N set by Justin Drake and other suggestions by other people is quite close to 3 of 5. So there are 5 major EL clients. So based on that, there should be 3 guest programs verifying of those 5 successfully. So that is why 3 or 5. And the fifth is one proof spans checkpoints to head. So this again is quite pre-alpha. We came to know about this just this Monday. So, and it is going to be specced out in the upcoming weeks. So we will try to integrate it once we have more information about it. Now the parts that we have not solved yet regarding that, Charles, next slide. So again, no hard fork, no consensus change. The only risks that there are, and which we are quite uncertain of, is what exactly the recursive spec is going to be like, because you have no info of it yet. And based on that, the whole spec is quite alpha. It's still in progress, pull request. So we are still actively monitoring the changes that are happening, as well as the checkpoint anchoring. How a node obtains a proof anchor to its own checkpoint is still unspecified. Regarding the proving window, right now, pre-gloss, the whole proving window is just is taking like 6 seconds, and the whole validation part for a block is between 3 seconds. So the time it requires ePBS so that the whole delayed execution things uh, works and the whole validation part shifts by 6 to 9 seconds. So it gives enough time for the proofs to be generated and propagated as well. For the verification to happen in attestations for the payload at the timely manner to get those rewards for timely attestations. Uh, the second last one is the concept DOS. Again, like I said, I shared that the size of the proofs are 4 megabytes, and it's still megabytes, sorry, and the execution for subnets might get flooded by requests, unnecessary requests, so it should be monitored, and there should be consequences for it, which are still being discussed. And regarding the test fixtures, the execution client specs are still being worked. They are working on the test fixtures. I We will share more updates on this in our upcoming weekly calls. So. Apart from that, you can go through our PR, which is currently open to go through the whole uh, proposal. And if you have any questions, we are up for it. Thank you.
Yeah, yeah. Can everyone hear me? All right. Let me just go ahead. Okay. Hi guys. So this is our presentation for the EPF cohorts. So we're working on ephemeral test net support for Reds and Lighthouse. Um, the fellows on this project is myself and Isaac with Mario as our mentor. So this is like what we're going to be talking about during the presentation. And so let's start with the specs. So what we're working on is EIP696, which is the ephemeral spec. So ephemeral is an automatically resetting testnet with deterministic genesis generation. So what that means is that it's a temporary test net. It resets every 28 days. So we have the genesis 0, which is the base state, and then we have the period I, which is like the current period for the for the calculation. So because this resets every 28 days, so we have the period I, which kind of resets, and we use this genesis states and the period for the current iteration to derive the new genesis to use, and then we run this every 28 days. So so this is like the genesis. This is like the genesis function, and then the reset function takes it up a whole notch, which basically like resets the setting again for the next iteration. So this is like the ephemeral cycle in summary, like kind of showing the how it works as a cycle. So this is the problem. So the problem with other testlets like Sepolia and Wholesky is that you have issues like state bloats because of these testnets accumulate states over time. So it makes it harder for like the testnets to sync, And then you have issues like testnet fault scarcity. So like issues like there's not enough testnet funds to like run validation. You have issues like validator set issues with probably because of inactive validators on the consensus side, and there's no clean testing space for new stakers. So this is running ephemeral today on Red and Lighthouse. You have to download Genesis and launch Node. Like you have to do this all manually, and then you run and sync it, and then this you have to do it again every 28 days. So you have to do like a lot of manual configuration, and then the reset happens, and you have to do this again and again. So this is what we hope that full native support will look like with our implementation. So we hope that simply when we are done with the project, we hope that when you run for Rets, for example, when you run Rets node, you just have to run Rets node chain ephemery and it works automatically. Same thing with Lighthouse, you just have to run Lighthouse network ephemery and it works automatically without doing a lot of other unnecessary steps. And the genesis is generated automatically, and you only need just one flag to run it, and the reset also happens automatically. We're able to detect when a cycle has passed for the next iteration. So this is the current state and gaps. So for Ret and Lighthouse, there is no native ephemeral support for Ret and Lighthouse. If you are to run ephemery on Ret and Lighthouse, you have to go through multiple setup and like multiple manual configurations, and it's stressful for the validators. So this is going to be our implementation approach for implementing ephemery for Ret and Lighthouse. So starting with Lighthouse. Uh, so for the Lighthouse, which is the consensus layer, so we are going to be getting the ephemery.yaml from the ephemery GitHub repository, and then and then we're also going to be using this to like do the update function, um which basically would basically update the variables that will be changing, because because like I said, ephemery is like a dynamic testnet. So we'll basically be overwriting some of the variables like the deposit chain ID, the network ID, the mean genesis time, and some other stuff. So and then from there we'll fetch the genesis.sszz file, that's the serialized file. So and then we validate this file and to check that this is like it's what we are supposed to be using, and then we pass this to the initializer to start. So along with this, along with the SSZ file, we're also getting the boot nodes and the default checkpoint sync URL. So and we're also going to be checking that the SSZ state matches with what we need for the current that is correct, is what we need for the current iteration. So this is kind of like going into what makes ephemeral implementation a bit different from other like network implementations like Sepolia and Mainnet, other networks from ephemery. So other networks have their config.yam as a fixed file, while ephemery has this with just the Genesis zero, and it's and we are this is not like we are not going to be using like just all of this ephemeral yam. So we are just going to be using some of it. We are going to be like changing some of the values in the ephemeral yam for the current iteration, and then other networks have a bundled Genesis or SSZ file already in the code base, but for ephemeral we cannot have this like we cannot have a bundled one that is like hard written in the code. It's already in the code base. So we are getting ours from the ephemeral repository. So we're also getting the boot nodes as well, and our Genesis validator route is also dynamic as well. So Lighthouse expects that we know some of all these values at compile time, but with ephemery, we can't know everything at compile time. So we have to calculate all of this first before and validate it first before we pass it on to the initializer. So I'll be handing over to Isaac to explain the rest part of the implementation.
Yeah. So quickly, just like Lighthouse, in Red we bundling the Genesis, the JSON, and be updating it into the Genesis struct. But since the Genesis, the JSON does not have constant chain ID and timestamp like other chains, so we have to do an update function to update the Genesis, the chain ID, and the timestamps. So not everything in the Genesis.json is changed. Some things runs across like different periods and iteration. For example, the alloc, the contrast stake, the for configuration does not change, and it's constant like every other chain. Just the chain ID and the timestamp do change, and that is what we'll be going to be updating with the update function before passing into the node launcher. It's like this. So what you have mentioned is the way that we're going to handle like the name chain in Ret. So in Ret, other chains like Minet and Sepolia, they have their chain ID kind of mapped to the name itself. But like I said just now, Ephemery does not have a constant chain ID because Ephemery ID chain ID do change every like 28 days. So you can't map a perfect chain ID to its name. So we're going to be fixing that. Instead of using the name chain, we're going to be using the chain kind ID to that is going to be working with a dynamic chain ID instead of a constant chain ID. So next slide. So as a secondary goal, we're going to be doing the reset function. So after a node launches, so after the Genesis configuration is done and a node launch, and after the 28 days elapse, currently the value any validator that is running like ephemery, we have to undo the whole setup. That's basically like switch up the nodes, clear up their database, and probably like reset, or they could just set up a config script to do that automatically. But it's not that in other chains because it's kind of like a stressful process and it's a bad user experience. So we are going to be automatically be detecting when a period expires, then stop accepting blocks, wipe the database, and reset it. But it's also worthy to know that many chains architecture does not support this, and that is exactly why we labeled it as a secondary goal. So some chain architecture does not support this state rollback, but we're going to be researching this on Lighthouse and Ret. So our approach is first we going to research how each client handle like shutdown and reinitialization. Aside that, we'll be doing a feasibility check to determine if runtime rollback works. And if it does, then we'll probably build a proof of concept. And if it doesn't, then we'll focus on adding the Genesis functionality. Next slide. So two key differences, sorry, not two, key differences between okay, sorry. Can you just go to the next slide quickly? So what do we consider success in this? So we are by the end of this project, we are saying that you could run Ret and Lighthouse with a single flag, and as well we could deterministically generate a correct Genesis state, as well that EL, that's the Ret and Lighthouse, could be compatible so that we can like bootstrap a full node out of the bus, and all text and fixtures are all working properly. So next slide. So quickly on our roadmap. So week 1 to week 5 is our research orientation, which has already exceeded. We're currently in week 6 and week 10, and we're currently working on the implementing the Genesis. Week 11 to 14 is our testing and validating phase, and as well we'll start researching on the reset functionality. and week 15 to 17, if the reset functionality is feasible after running the feasibility test in week 11, 14, we'll focus on building the reset POC. And in the last 2 weeks, we're going to wrap up build documentation and getting our PRs matched. So thank you all. And any questions?
Yeah, sure. Is my screen visible? Okay. So let's go. I'll keep it short and concise. So, hey everyone, I'm Mohit Grover, and my background is mainly in Ethereum protocol engineering, and I'm exploring system design and improving Rust. So, for this EPF cohort, my project is Ream black box interrupt testing, and the goal is simple. So, make XMS's signer state failures reproducible in Hive. And this is not a consensus code project. I'm building the testing infrastructure needed to expose a new class of client failures, which is introduced by lean consensus. So so let's understand what's changing in the first of all in Lean. So the current signing state model is BLS. So BLS can be used almost every time. So it's a stateless signature and it does not remember which slots it's already used. But Lean consensus changes that. It is a slot synchronized key state. So a one-time material is consumed by the slot, and here the persistence becomes consensus critical, like it's required for the safety. And the invariant is that one key combined with one slot, we should at most produce one distinct message. This is something that can't be changed. So on this is the infrastructure on which I'm building. And what while going through the my research, I figured out the missing test is at the signer boundary. So there's a difference between receiving equivocation and creating equivocation. So currently the lean spec allows you to have two blocks which at the same slot. So it lets the fork choose decide which block it should continue with, but it says nothing that two blocks should not be produced. So this is a signer state thing. So Hive must ask the validators to create two requests with slot N and a body A, and again with the slot and body B. And now it depends on the client side how it should react to that. So and the major motivation of this project is to turn the DevNet failures into permanent Hive tests so that other in the future it won't make change. So the current status of the project is I majorly surveyed three areas, which is XMS's lifecycle, aggregation, and state comparison. And I settled down to XMS's lifecycle as my primary anchor. So I first of all corrected the test model, which is I would be focusing on the signer state, not on the receiver side. And I have landed the Hive groundwork for now. So I have made a PR for a shared validation setup for adding more test cases. And I've also added the validation test cases just yesterday. And the PR is under review for that. And the future would be creating a smallest common signer state request response contract with a reference adapter. So this I will be discussing with Richard to come up with a common schema so that everything can be built upon that. And the major two cases are the proposal non-reuse and key exhaustion, which I'll discuss now. So this is the major schematic diagram which discusses the test. So basically the non-reuse test is where two different proposal attempts are made at slot n, and the acceptable outcomes is like this: the client could refuse it, it could return the already cached block A, but what it must not do is allow two distinct valid signatures to pass. And the second test is exhaustion. So for the exhaustion, currently the life cycle of keys is pretty big, so I would need to have some mechanism to have short window keys, or maybe just reach the edge where the life cycle of key is about to complete. And I'll allow the test to advance beyond its active range, and then I have to measure the edge cases, like it doesn't start back from the again, and it gives a concrete bounded refusal, and the client stays healthy. And this validation setup, it's already being done. So this is my timeline. So the first initial weeks will be about auditing the contract and making the schematic with Richard. And in the stretch goals, I have the aggregation. For that, I have a go no go like contract. So if the conditions fall in my criteria, I will proceed with it. If not, I will not. And the 3 to 4 would be conducting the signer path with the reference adapter and short window keys. And the 5 to 9 weeks is about the core project. So it will be building the non-reuse test case and the exhaustion test case. And after that, I would be hardening the client matrix. And if time permits, I'll reach out to the stretch goals. So that's it from my side. The main area is to observe failures from DevNet and produce them as Hive tests, and so that the regression doesn't keep on going permanently. And the minimum success is mentioned, which is reusable signer path and non-reuse and exhaustion tests is merged with validation test suite completed and reproducible results. Thank you.
Hi everyone, I will be sharing my screen and keeping it concise. Actually, I have two project presentation, but on one of the projects, Samir, who is my fellow contributor, is not well, so we will not be presenting today on that one. We will do that async. Is my screen visible with my cursor? Okay. So hi everyone, my name is Sagar and my project is on Aragon for implementing SSG query language. And my mentors are Tamagna and Eaton. So what's the problem right now? What before discussing the query language, let us discuss why it's needed. So currently the problem is that we have currently fixed RPC methods like if, get balance, and call and get logs, right? There is no one query endpoint so that we can get all types of data from that. We cannot select any generic type of data, like for example, if we want to filter the data or get only some specific subset of the data. These are the two problems. And then we have that these methods do not actually return any proofs right now. So our only option is to trust that the client is returning valid data. So here's the gap. As I said before, currently we cannot select the fields that we want. And secondly, we cannot filter the data based on some fixed criteria that we have, the condition that we have. And again, proofs, we only if get proof is used to get proofs for account and storage slots, and for rest of the data we cannot get them. So currently prior work has been done on the CL side only on Prism by June Song in last year's EPF. So and this year it will be implemented in Aragon by me. Yeah. So here's the solution. I will be implementing a new endpoint in Aragon's RPC layer, and this actually will be a query object, not a method name. Like you can build your own query and then send that query to the Aragon client. And if you want, you can request for the proofs too. It's also optional. If you don't want the proofs, then you need not ask for it. Okay. So here's the structure for the query. First of all, we have anchor. So what happens in the anchor is that we are passing a trusted node. So the path that will be passing to the query language will be related to this anchor, and we already know what is the anchor's hash value. So we can already compare the hash tree root generated from the later proofs to be compared against this anchor. Next, we have the path. So this addresses a location in the anchor tree for which we want to query. All right. And next we have filter. A filter is a statement which filters out from an array or from the queried results. For example, if gas price has to be below a certain value, or the two value of transaction should be something, then we have summaries. So what is a summary is that it replaces a subtree in a Merkle tree with its hash tree root. And alias. An alias is equivalent to a variable in any programming language. You can query something and then store it in a variable, and then use that variable to reference the result in a later query. In the same, in the same query, but in a later block. Okay, so how are we actually getting the proofs? Let us understand the structure. Suppose this is our anchor root, and we want to query the data on this node. I hope my cursor is visible. So this is the query node. Now, for to compute the queried node's parent node, we need the witness node here. So the witness node hash is actually a summary of the entire subtree of the sibling node, and using this witness and the queried node, we can just hash them together to get the computed node. In the same way, after we get the computed node, we again need a witness from its sibling node, and then we can hash them together and to get the anchor root. So after getting the anchor root, we can compare the two. If the two are same, then that means the data that has been returned is valid and legit. So here's the roadmap. Phase 1, 0 and 1. So first of all comes the endpoint setup. This phase has already been completed. It registered the root in Aragon's RPC layer, and since all the RPC roots of Aragon currently has coarse handling and optional compression, this our API is also capable of that. Then currently I'm in phase 1, in which I am implementing parser. So I have already implemented the filter parsering, and I'm currently working on parsing. Like, we are passing some data, and the query is parsing that and sending out dummy responses for now. So the next phases will be on wiring up. So as we know that currently Aragon does not have execution blocks, and Jack is currently implementing that. So after that has been completed, I can wire up the API with the execution blocks to actually fetch real data and completely eliminate the dummy data. Then after this, after phase 2, we have got a point where we are actually getting real data, but we are not getting any proofs yet. So phase 3 focuses on proof generation. So in this phase, we can actually set the flag for generating proofs, and we will get proofs back from the client. Then phase 4 and 5 are completely related to testing and documentation. First of all, I will write exhaustive test cases and see that whether it is fetching the correct data and whether the proofs are valid. And then we will also run kurtosis devnets with other clients, and after running the client for some time, I will be testing if the proofs and the query implementation are working correctly. And last but not the least, our documentation phase, where I will be updating the Aragon documentation with the semantics for the language and how to use it. Yeah, so these are the challenges. As I said earlier, it depends on EL blocks, which are currently being worked on by some other Jack. So until then, we will be depending on dummy data. And the next is that there is currently no formal EIP for the query language. So for query language, I have written my own proposal, but as the project moves on, the requirements will obviously evolve a lot. So the code will stay the same, but a lot of things will be changing. And then, yeah, the final challenge is proving filtered results. So the thing is, we can prove any node right now using the proof mechanism I told you earlier. But how are we going to prove the filtered results? Like, it's not a complete node or a complete data that can be hashed. So we need to actually figure out a way how we can, whether we need the hash for the entire result too, or we need to, as a proof, we need to fetch the entire result as a, and get that on the uh, client side for the caller of the API. So deliverables. First of all, the core fields proven, like the transactions has from to value and the headers. And then if this is completed within the time, we will complete the surface, so that all the across the remaining fields, all the remaining fields can be queried. So yeah, that's it from my side. Thank you.
Yeah, yeah. Yes. Okay. Can you see my screen? Okay. Hi, everyone. Richard here. So my project is about the spec test that decide whether a lane consensus client conforms to the specs. So I will show you a gap I found in those tests and my plan to close it. So the Lean Consensus 2026 plan calls for a stable DevNet with 5 or more distinct clients, monthly DevNet launches, and a long-running 10,000 validator DevNet. And every one of those goals rests on the same constant, that independent clients must compute identical state transitions. So the spec tests are the tool that is supposed to guarantee that before anything reaches DevNet. A quick refresher on how conformance testing works today. The Python spec generates fixtures that record a pre-state with some blocks and the expected post values, or in some cases, an expected error. Then the Hive lane simulator replays each fixture against each client over HTTP, and the harness compares the client response to what the fixture pinged. And here is if the finding that motivates the whole project. Of the 45 state transition fixtures on DevNet 4, everyone pins the post slot, but only 5 pin the state root. And and for the other 40 fixtures, a client can compute a completely wrong post state and still pass the test. In definite 5, the figure is growing, is 5 out of 59. So the discrepancy is rising as time goes. And there other gaps are found in the fixtures too. The post response fields, pins fields such as justified slots and latest justified slot, but the current schema design cannot support them. So the harness ignores those checks. Now, this is the current state of the schema, and that needs to be improved. I'll try to be fast. So why does this matter? A state divergence bug creeping into DevNet is one of the immediate risks. If it slips through, it surfaces as a, a, a bug that a state divergence bug on a 10,000 validator DevNet, and it can result to a multi-client team effort to localize across 5+ clients. But if caught by a fully pinned fixture, it's a single line CI failure that points to a client and a fixture scenarios field. The plan for the project has three pillars. First, I audit the pinning across all three fixtures families, frog choice, and including frog choice and verified signature and DevNet 4 and 5. And if there are gaps in the fixture that, if not pinned, will result in bugs, I tighten the generator so LinSpec always pins it. And that process is nearly free at generation time. And thirdly, I enforce the pin fields in Hive. And for state transition fixtures, it means widening the schema to enforce it. The timeline of the project runs from now up till DEFCON. So by mid-August, I plan to complete the audit and share the audit report with the fixture authors to get some feedback, and then submit the first batch of PROs to comprehensively pin the fields. And then also co-design the contract schema with Mohit, who is also working on a black box interrupt test for Hive. Then in early September, I enforce the enforcement should be merged into Hive. Then final report and presentation towards the end of the roadmap. So I'm not the only fellow working on enhancing testing, like I mentioned earlier. Mohit is also working on testing XMSS signer state failure mode. And our proposals interlock, which is designing the driver schema for state transitions. The mentors for this project are Derek and Kobe from RIM. So where things are stand now, so I built and ran the simulator against the real clients, audited the DevNet 4 and 5 state transitions collections, where the numbers came from, and I validated the direction of the project with my mentor. And the big ask now is for me to publish the report and get the feedback from the fixture authors on the next direction. So, thank you, and any questions?
Again to everyone who did these presentations. I think it's exciting to see you diving into so many cool projects now, and yeah, just can't wait to see what is happening actually. Can't wait to see this being executed. So, good luck with all of your plans that you presented these days. I wish to see more in your updates coming forward. Um, One more important update is that next week we are skipping office hours call, so there will be only the Monday stand up, and we will go back to the office hours calls on 19 with another AMA with group core devs. So going back to the regular AMAs, basically the standard office hours. So thanks so much for all the presentations again. It was very exciting to see it today, and thank you so much for the couple of you who managed to stay till the very end. And yeah, Richard, thanks again so much. You managed to do the very last one, so yeah, thanks a lot, man. That was great. Yeah, thanks again, everyone, and I wish to see you next week. Looking